TCP/IP internet layer. That's what we want to spend some more time focusing on now. I mean, after all, as I said earlier, this is one of those layers where we make our money. Yeah. The internet layer coordinates to what layer of the OSI model? Yeah, the one you see glowing there in that great graphic, it is the network layer. So, let me back up actually. I'm going too fast here. So we're talking about the TCP/IP internet layer, and this coordinates to the network layer, as we know, of the OSI model. Now let's take these characteristics of this layer one at a time, okay? The first is that it is connectionless. It is connectionless, meaning it is not reliable, the stuff that goes on at the network layer. You see, the network layer says, look, if you want reliability, do it up here, do it down there, leave me alone. I've got enough to do with just figuring out how to move traffic from one segment to one segment. I don't want to be involved with any overhead of connection-oriented communications. Packets, therefore, get treated independently. Now, what is the addressing that we have at this layer? The addressing that we have at this layer is hierarchical addressing. It consists of a network portion and it consists of a host portion. Hierarchical addressing. Okay, network portion and host portion. And we're going to get into this, as you might guess, in much greater detail. Okay? But suffice it to say, when you see an IP address like 192.168.1.100, there is going to be a portion of that address that represents the network and a portion of that address that represents a particular host on that network. Notice, best effort, no data recovery, media independent. The network layer just doesn't care about reliability. It's busy with these IP addresses and routing the traffic using the IP address from one location on the globe to another location on the globe. And we'll get into these IP addresses in much greater detail later on in this course, but I just wanted to preview them for you so that you know that they are a two-part address, the network part and the host part. Now, a very, very simple analogy here is your street address. Yeah, you have a street that you live on, and then you have a house number. I was born on Jones Street. No kidding. So the street I was born on was called Jones Street. And we were at 3 Jones Street. So there was the street that I lived on, and then there was the particular unit number so you could find me on that street. And that is exactly how we are going to see that IP addresses work. Remember I told you that there was that process we call encapsulation? And that there would be address information attached to the data? Well, here you're looking at all of the various fields of information that the IP protocol attaches to the data at the network layer. And look at this. We saw it in Wireshark, and now we're seeing it here in this pretty graphic. One of the pieces of information is the source IP address, and another piece of information is the destination address. So we have source address and destination address, IP addresses, as part of the information that's appended to the data by the network layer. So you probably never think of it this way, and I don't blame you. You're not a computer. You probably never think of your address assigned to your computer at layer 3, that IP address. You probably never think of it as a 32-bit number. No, you don't think of it as a series of ones and zeros. 32 ones and zeros. But that's what your computer does. That's how your computer sees that IP address. You see, for readability, for the convenience of humans, they invented dotted decimal notation. But the machine, the computer itself, sees that IP address as 32 bits. Bits with a on or off setting, 1 or 0. What did we do for readability? The first thing we did was we broke that number down into 4 parts, each consisting of 8 bits. What do we call these 8 bits? An octet. So we have 4 octets that make up the IP address now. To further make things convenient, we convert each octet to decimal. We convert each of those 8 bits to a decimal representation. And then finally, we put a period in between each of those decimal representations to help define the octet. So we have 172.16.128.17, and this is the representation we use as humans for that 32-bit binary number that the computer utilizes. Now, Isaac just typed in /24. Be careful. You are referencing the subnet mask, and we do not see that represented anywhere here. So make no assumptions. Okay? The subnet mask is 32 bits, and it is made up of zeros and ones, and it is broken up into 4 octets, but we are not discussing the subnet mask. Okay? So, no assumptions. We are looking at right now how an IP address is represented. Now, when they first invented IP, they went in and they created address classes. And they said, okay, look, this is how we're going to do this. We're going to create a Class A address space, and this Class A address space is going to be for huge networks. We're going to force the first bit position to a 0 in the IP address. And when we force the first bit to 0, that'll signify a Class A address. And just these first 8 bits will be for the network. And then we'll leave all the rest of these 24 bits for the identification of hosts. So when you look at that, you say, wow, with a Class A, there can be just a few networks, but each of those few networks, each of those street addresses can accommodate a huge number of houses, house addresses. Yeah, think about it. There's 8 bits for the identification of streets, but on each of those streets, there's a lot of bits, 24 bits available for the identification of houses on those streets. Interesting. They created a Class B. And what they did was they forced the first 2 bit settings to 1, 0. This would signify these 2 octets, 16 bits, for the identification of streets. And this would allow that equal number, 16 bits, for the identification of hosts on those streets. You can see where they were going here, medium-sized networks. And then they said, let's create IP addressing for small networks. And this is our Class C. The first 3 bit positions are fixed to 1, 1, 0. This had the first 3 octets, 24 bits identifying streets. So lots of different street identifications here, but only 8 bits for the addressing of houses or computers on each of those streets or networks. Wow. Very interesting. Now, you might ask at this point, is there a Class D? And the answer is yes, there is. And Class D addresses are something we'll get into later on in this course. It's for multicast addressing. And there's even a Class E, and it was reserved for experimental purposes. So in this class, we are obsessed with the A, B, and C classes for addressing networks and hosts. Now, if you do the math on these bit manipulations that they did, you can come up with the decimal value for every single one of these address classes. For example, if you force the first bit to a 0 value, if you force the first bit to a 0 value, then in the remaining bits, you can have 0, 0, 0, 0, 0 through 1, and then all ones with a 0. Okay, so I mean, you've forced the first bit position to a 0. What does this work out to in decimal, what we care about? Class A addresses will have the first octet be numbered 1 to 126. One to 126 in the first octet. Now, Class B has a possible range, and it's 128 to 191 in the first octet. And you look at this and you go, wait a minute, 127 is missing. Well, the interesting story here is 127 they reserved. They reserved it for loopback purposes. Okay? Loopback purposes means for internal testing. If you go to your Windows machine and you ping 127.0.0.1, your machine responds, telling you that TCP/IP is properly initialized on this machine. So the 127 Class A space was reserved for testing purposes. I chuckle when I say this because it's clear when they designed TCP/IP, they never ever dreamed there would be an address shortage. They sacrificed a Class A address for testing purposes. That is clear evidence that they never in a million years dreamed that we would have the address shortage that we do. By the way, remember I said the first octet's value would be from 1 to 126? Right? And then we'd skip 127 and we'd have 128 to 191? Remember when I also said that with Class A addresses, we would get a few addresses, a few networks, but each network could have a large number of hosts? Look at this. When you have 24 bits left over for hosts, you get 16,777,214 host addresses. Imagine that. Now, a Class B address beginning 128 to 191 is for the medium-sized environment. You have 16 bits for hosts, so sure enough, you can only accommodate 65,534 machines on that network. How about the Class C? Well, the Class C has its first 3 bits forced to 110, and when you do the math, the Class C range is 192 to 223. You only have 8 bits left over for house addressing, so you can only have 254 hosts on that particular street. Is there a lot to memorize on this table? Sure there is, and that's why flashcards come in really, really handy. By the way, as you might guess, you don't need to bother with this middle column. Yeah, you don't need to bother with all the permutations of the bit settings in the middle column. But this column of recognizing an address class by its first octet is certainly valuable. And knowing roughly the number of hosts, roughly, you don't have to memorize them exact, but like if you were to ask me, hey, how many possible hosts on a Class A network, I would tell you roughly 16 million. If you said how many on a Class B, I'd say roughly 65,000. And if you said how many on a Class C, I would be able to tell you exactly 254. And I'll actually show you later on in this course how you can calculate that number precisely. So, lots of you right now in the queue, in the chat queue with our mentors, are talking about subnetting and what about this and what about that. And you're jumping ahead, and I don't know what to tell you. Okay? Trust me that I know what I'm doing, and trust me that we are going to get to all of those subjects that you're excited about. Okay? It's just that, as you know, we have many students in here that are brand new to networking. So they literally knew none of what is on this chart, and that's why we go through it so slowly and so carefully. And you guys are being very funny in the queue. I love it. Oh, you guys are great. Great comments right now. The one thing I can't stand about the instant replay, the replay product, is that the replay students don't get to see any of the great chat that's going on right now. So everyone's saying, we trust you, Anthony, we trust you, and we just want to go, we can't wait. We can't wait to get to that other stuff. Just please be patient. We'll get there. All right. Great stuff. So here's something I'd like to do right now. I do want to jump ahead here for a second. Okay? Let me just jump ahead for 1 second. All right, watch this. You see this Class C address? We say on this chart that on a Class C address, you can have 254 host addresses. Okay. Let's see how that's calculated. Here's how it's calculated. There is a magic formula called 2 raised to the number of host bits minus 2 that'll give you the number of hosts on a network. We'll call this capital H. Okay? So 2 raised to the small h, that's the number of host bits, minus 2 equals the number of hosts that we can have on the network. Okay, so if we plug this into a calculator, we know there's 8 bits that we have in a Class C for host addressing. So if we do 2 raised to the h minus 2, we come out with an answer of 256 minus 2, and sure enough, H equals 254. Now, lots of my students know all about the magic formula. But what's interesting is, why the minus 2? Well, let me answer the minus 2 in the formula for you. It subtracts the case where all of the bits are zeros and all of the host bits are ones. And great job to Steve in our chat queue. Yeah, that's right. This identifies the network you live on. It's like 0 Jones Street, right? No such thing as 0 Jones Street. And then this, the all ones in the host bits address, this represents the broadcast when we want to communicate to every house on that street. So we subtract 2 because we cannot address all zeros in your hosts, and we cannot address it so that there's all ones in your host portion. Now, there is the concept of a local broadcast versus a directed broadcast. You see, this right here is an example of a directed broadcast. We're saying, hey, for the 10 network, we want to send something to everyone. This, filling the entire 32 bits with ones as a destination address, this is called a local broadcast. So, local versus directed broadcasts both exist. And want to know something really interesting? Cisco routers, like most routers out there on the planet, they drop directed broadcasts by default. They don't allow this behavior to go on in their network. Why? Security reasons. There are many, many security attacks that take place using directed broadcasts. So they turn off that support capability and they only allow local broadcasts. We know that 127.0.0.1 and in fact the entire 127 address space, so 127.0.0.1 through 127.255.255.254, that's all reserved for testing purposes. And let's remember another address that's reserved in our environments, and that's 169.254//16. What is this address, 169.254? It's the AIPA, the Automatic IP Addressing Scheme. And this is what will happen on a Microsoft box. I'm pretty sure they invented it. This is what happens on a Microsoft box when you can't get an IP address from your network administrator or from a DHCP server. Your machine will automatically configure one from this address. Mike Vasquez, our celebrity guest expert in the queue. Mike, you probably know if that's a Microsoft invention or not. I know it has become a standard, but I'm pretty sure it was Microsoft that initially started doing that. Mike's chatting in with us. I know it's now a standard and everyone adheres to it. Okay, and sure enough, Mike's confirming that they were the first to widely implement that approach. Pretty cool. Okay. Wow. We're just scratching the surface, And we are learning so much about these IP addresses. Now, there's probably something that you've heard that's kept you awake at night. And that is that we're out of IP addresses. And the answer is, yeah, we are. Once we started to run out of addresses, all of the internet standards organizations, they all got together and they said, we need to solve this real quick. And one of the band-aids that they applied to that situation was to go and reclaim some Class B addresses, a Class A address, some Class C addresses, and reserve those for private use only, so that we could duplicate their usage again and again and again in homes and in offices and everywhere outside of the public internet. Wow. Here to tell us more about this reserved address space concept is our guest expert, Doug Bassett.
We have a problem. We are out of IP addresses. And as you know, every device on a network has to have an IP address. But back when they came up with IP addressing, they're like, oh, it's just going to be the Department of Defense and maybe a couple of colleges. That's why they use 127.0.0.1 to ping yourself. And unfortunately, that 16,777,000 and some odd addresses, they just flushed them away because, there's plenty, we can always make more. Well, we're out. We are officially out of regular IP addresses. But every device and every network needs to have an IP address. If you have a refrigerator that hooks up to the internet, and don't laugh, I've seen them, you got to have an IP address. So what do? Well, we're going to use what is called a private IP address range. This private IP address range is still a valid IP address. It can still go from device to device to device, but it has a unique characteristic. It is not routable on the internet. Simply isn't. If it sees a packet that's supposed to go to one of these private IP addresses, the router will simply say, well, this is an invalid address, and it'll just throw it away. But how does it work internally? Well, it works just like any other routing IP address. Checks a routing table. Hey, do I know how to get there? Yes, I do. Boom, there it is. Away it goes. You do need to memorize the range of addresses. We have a Class A, we have some Class Bs, we have Class Cs. Memorize the ranges. You have to know them. The most popular range, of course, is the 10 address range. Chances are, unless you're in a home environment where you're using a consumer level device, you are using a 10 address range because it gives you 16,777,000 some odd addresses, and they're free. And then you can break them up by Class Bs or break them up by custom subnetting or whatever you'd like to do. But memorize the range. It's 10.0.0.0 to 10.255.255.255. This is what you're going to see the most of. We also have 172.16, Class B to 172.31.285.255. And again, these are Class B addresses. But 172.16, it's kind of a weird number. And if I can have 16,777,000 of something, or only 32,000 of something, why would I go with a smaller number? And yet, sometimes you are going to see this. Now, 192.168, it's a Class C address range. The thing about 192.168 is you really shouldn't use it in any environment at all, in a corporate environment. If you're going to do it in a home environment, that's great, because most of those consumer level wireless access points, or if you get like a cable modem router or something like that that automatically hands out IP addresses, it's going to hand them out in a 192.168 range. This is also used by what's called automatic private IP addressing, or a PIPA, very popular with Microsoft systems. So if everybody's using it, what's the big deal? Well, 192.168, if I'm in a corporate environment and we have security and firewalls and all that, and we're not allowing wireless, maybe we're doing certain things to allow wireless, you may have somebody go out to a consumer electronics store, buy a wireless access point, plug it in, and then it just automatically starts handing out IP addresses of 192.168. So if you see 192.168 in your environment, that's a huge flag that says somebody dropped in an unauthorized consumer level device. And that will make it a lot easier for you to troubleshoot and hunt the stuff down and so on and so on. So again, these are the ranges. You need to memorize them, but don't use, in my opinion, anybody but the 10 range. Now, of course, if you already have an environment and it's already configured and you have to use 172.16, okay, that's what you got to use. That's what you got to use. But again, we run into the problem. If this is something that doesn't route to the internet, how do we get to the internet? I mean, I'm at home and I'm on a 192.168 address. How am I getting to the internet? Well, they have this device that you're going to learn how to configure later called network address translation. And what network address translation does is it has a real live IP address and it converts it to our private addresses, sends the traffic inside. When it has to go back out, it goes back to the NAT device, which translates it back into the real live IP address, and it keeps track of all this stuff. It's pretty cool, and you'll see it a little bit later. But again, you need to make sure that you memorize these particular ranges of addresses, and my recommendation, try and stay within 10.
Well, great stuff. Thank you so much, Doug. So memorization, the Class A private address space that was reserved. It's easy to memorize, isn't it? Because it's the entire 10.x range. Yep. It's the entire 10.x range. In fact, that's how we often refer to it. We just say, oh yeah, I'm numbering in the 10.x, right? 10.x, 10. anything. That entire 10.x range Class A network space is reserved. Class B, little trickier to remember. You got to remember the number 31, right? Yeah, specifically 16 to 31. So notice just some of these networks, Class Bs, were reserved, or a few of them, 172.16 to 172.32 is reserved for the Class B address spaces. And then for the Class C, it's all of the Class C addresses that begin 192.168. Okay, so 192.168, whatever, that is private address space. And Doug did such a great job of describing for us how this is often utilized by consumer-grade devices. So a lot of times we'll see this in home networks, and a lot of times corporations will use 10.x because of the tremendous flexibility they have and the tremendous number of addresses that are reserved. Doug also did a great job of conveying to us how these private addresses must be network address translated to public addresses if you want to communicate on the internet. So when I started this whole thing about private addresses, I conveyed to you that this was all a Band-Aid, and network address translation and these private addresses is indeed a Band-Aid for the shortage. What is the main solution? Not necessarily the final solution, but what is a solution that is slowly making itself more pervasively implemented out there? Well, of course, it is the next generation of IP, IPv6. We've been talking about IPv4 up to now. And you might say, what happened to V5? Well, V5 was just experimental and never implemented. So we're going to be going with two versions of IP now, V4 and V6. And we're already running both of these in environments right now. I mean, it's really funny. if you look at your Windows machine, this is a Windows 7 machine, and I do that ipconfig/all, we can see that this thing is already doing IPv6 stuff. So IPv6 is there already. Now, we know so much, we've learned so much about IP addresses already. How do they typically get assigned to a machine? Well, that's with DHCP. Yep, DHCP, the Dynamic Host Configuration Protocol. And there is a 4-step process that is used for DHCP. Yeah, a 4-step process. And this 4-step process is detailed as follows. The first step is what's called the discover message. The machine comes up and says, "Help! I need an IP address so that I can communicate on this network." A machine, a DHCP server, hears this and says, "Okay, I will send you an offer message. Here is IP address information that you can use. I am offering this information to you." The receiving machine of that offer can then say, "Okay, I would like to request that information." So it sends a request message. And finally, the server responds with an acknowledgement. Now, this is pretty tricky to remember. So the acronym that I have always used, the mnemonic device, that I have always used, and many of you have already commented on because you know I love to use it, it's DORA. Yeah, an easy way to remember this 4-step process is the American cartoon Dora the Explorer. Great way to learn Spanish, by the way, if you're 5 years old. Okay, so DORA. Yeah. D, a broadcast discover message. O, an offer. R, a request. And A, an acknowledgement message. This is our 4-step DHCP process. Another key service that we have with the IP system is DNS, the domain name system. Think about it. When we go to our web browser, we don't type in an IP address when we want to get to cisco.com. Yeah. We could if we knew that IP address, right? In fact, watch this. I just pinged cisco.com. I just pinged cisco.com. Okay, ping cisco.com, and I got the IP address of Cisco, one of their many IP addresses for the hosting of their site. This one I hit was 72.163.4.161. So I can go to my browser, 72.163. What was that? I have short-term memory issues. 72.163.4.161. 4.161. And we'll hit Cisco. But my goodness, who in the world wants to get to Cisco's site that way? I want to just say Cisco in my browser literally just Cisco, and I want the www and the .com and all that filled in for me, and then I want my machine to go find that address. And what service does that for us? It's DNS. The domain name system translates those names that we use in browsers called URLs, Uniform Resource Locators. It converts those names to IP addresses for us when we are utilizing IP over the internet. And sure enough, we fill this information in, don't we? We fill this information into the network config of our workstations. We either get the information automatically for IP and for DNS, or we go ahead and we fill this information statically in these various screens. How do we view this information real easily? Well, I kind of already alluded to that, didn't I? We use ipconfig when we're on a workstation. Yeah, that is the easiest way to bring up the command prompt on your workstation, Windows-based, and just do ipconfig. And it will quickly tell you, look, your IP address is this, your subnet mask is this, your default gateway is this. And remember, ipconfig/all will give you even more details of your configuration, including your DNS servers. So what we will see is detailed information with ipconfig all.